Hey guys, this is my first time ever making a math explaining video, so shout out to the person who was the first to request this topic. Remember, if you want a math video on a topic, just send me a request and I'll make the video. So, without much further ado, let's get right into related rates. So, related rates is the idea that a bunch of quantities and their rates of change are related, and we have to know some rates of change and some quantities to figure out some unknown rates of change. So let's do an example that's pretty common in schools, I'd say. So let's say we have a corridor here with a right angle intersection, and let's say in this corridor we have a super senior trying to get with a freshman. Now, the freshman is running away at a rate of 3 meters per second, let's say, and the very determined senior is chasing at a rate of 7 meters per second. So let's say at this instant, the freshman is 8 meters away from the corridor, from the intersection. The super senior is 6 meters away from the intersection, and we want to find what is the rate of change of the distance between them. So that is our unknown here. So after this setup, the first step in a related rates problem is to know exactly which variables we're talking about. And everything here is a variable. I'll draw a simplified model here for convenience. So senior, freshman, and a right angle here. So the first we want to know what exactly are we trying to find. We don't know the distance between them at this point, so let's call it L. And all we want to find right now is dl over dt. What's the rate of change of their distance? So, and we know that also the senior is 6 meters away from the intersection, but we don't plug in the numbers yet. We want to write everything as a variable, and you'll see why very soon. So let's just call this little s. And the same thing, we don't write 8 meters here, we call that a little f. So now we have a bunch of variables. Why are we doing this? The second step is to relate the variables first. And just as a side note, we know we also have ds over dt and df over dt. They're given over here, and we'll need that later. So again, let's go back to finding a relationship between the variables. So usually it'll be some kind of like geometric constraint, like the area formula or something. Right now what we have here is we have three sides of a right triangle, so you can use the Pythagorean theorem here. At any instant, this equation is true. L squared equals s squared plus f squared. Now you see why we're going to be doing this, because we are going to take the derivative of this equation that is true at any point, and therefore the derivative of this equation is going to be true at any point also. However, we want to take the time derivative. Let's see how it works on the left side first. So for the derivative of L squared, we could say it's 2L, but since L is a function of time, and we are going to take the time derivative, we need to remember the chain rule. Like we've always done in implicit differentiation, we have a dl over dt here. Similarly, on the right hand side, we do 2s ds over dt and plus 2f times df over dt. Alright, now we're cooking because we have all of the variables here. Let's look at the right side first. So 2 times, okay, now we can go back and plug in our s. 2 times 6 times, but we have to be very careful here. Remember, this super senior is running at 7 meters per second, but he's running towards the intersection. So the distance between him and the intersection is actually decreasing at 7 meters per second. So you have to plug in -7 here. And do a similar thing with a freshman. She's 8 meters away from the intersection, and he's running away at a rate of 3 meters per second. And we're not explicitly given L, but we do have this equation here. L squared equals, now we plug in 6 squared plus 8 squared. So L squared equals 100, giving us L equals 10. So we go on the left-hand side, plug in 10 here, and we don't know dl over dt, but that's fine because that's exactly what we're solving for. On the right-hand side, you plug in all the numbers, you get negative 84 plus 48, which is negative 36. And that, 2 times 10, is just 20. And now we solve for dl over dt. It gives negative 36 over 20. You have to be very careful of the signs here. Every positive or negative matters. And you get negative 1.8. And we fill in the units now. L has a unit of meters, time has a unit of seconds, so our rate of change is negative 1.8 meters per second. Now we interpret it based on the problem. So we want to find the distance, the rate at which the distance between the freshman and the super senior is decreasing at this moment, or changing at this moment, so we say decreasing at a rate of 1.8 meters per second. So we usually don't want to talk about a negative number. We're talking about a rate of change. A much better way of saying it would be decreasing at this positive rate of change. So as a quick summary, when you're doing related rates, you want to make everything a variable first. Write down every variable that you might want to know or that you already know. And next, find a relationship between the variables. And next, you finally take the large derivative regarding that earlier relation that you found. And you will get a bunch of numbers that you already know, such as s here, f here, ds, dt, etc. And you'll usually end up with only one rate that you don't know, and then you can solve for it and then interpret it. So if you enjoyed this video, or if you found this helpful, please request another topic and I'll gladly make a video based on that topic. Alright, see you guys soon.